Let us talk about guard bits and truncation. To understand guard bits, let me take some two examples of floating point numbers. So floating point number 1, floating point number 2. Here these two floating point numbers are assuming 3 significant digits. Okay. So what is the meaning of 3 significant digits is, I will tell you. Here you have 3 digits at most to represent your number, right? So this is called scaling factor. Did you remember? So the number of bits we use for mantissa is called significant digits. Okay. So here mantissa is represented by 3 digits, correct? 2.95. Correct. So in our IEEE 754, if you remember, we used 1.m format. Did you remember? Base power exponent something minus 127. So here this number of all these bits are called significant digits. So we were representing 23 bits for mantissa, correct? Plus this implicit bit. We don't represent it, but it is there. That's why 23 plus 1, 24. So we are using 24 bits to represent mantissa in our floating point numbers, which are IEEE 754 floating point numbers, correct? So the more number of bits we have, more precision we get, more accurately we can represent some data, correct? Example, if you want to represent 1.99999 like this. Okay, so some 100 nines. Can we represent with only 3 significant digits? Then you can write only 1.99. Okay, so you can't do more than that. That's why, so with 3 digits, we can have only some accuracy. The more accuracy if you want, more significant digits you require, but it consumes more space. That's the trade-off. Now assume that let's say we have 3 significant digits. And one more thing, I am not allowing 0 in this position. Why? Exactly like, why we used 1.m representation? Same reason. When you write 1.m like this, first digit is 1, which is non-zero, then automatically your numbers will become normalized. Then every number will have unique representation. If you are allowed to write 0 here, then what is going to happen is, so people will be writing like this: 0.01 into 10 square, which is 1, then 0.10 into 10, which is 1, 1.00 into 10 power 0, which is 1, right? In that way 1 will have multiple representations. To avoid that, we have to normalize it. That's why the first digit from now onwards is non-zero. Okay, so in this model, now I would like to talk about guard bits. Generally we use guard bits to store the intermediate results. Example, let's say you are doing some calculation, maybe addition, otherwise subtraction, whatever it is. When you are doing that, then sometimes what happens, your result will go beyond these digits, correct? That means the number of digits should be more to represent it. Then there are two options. Simply cut that part. That means, while doing the calculation, whenever your calculation goes more than 3 digits, then the remaining digits you simply skip it, ignore them. That is one thing. Then we say that we are not using guard bits. When you use guard bits, then we know we will be having more digits. That means we will be adding extra digits to represent that, I can say that to represent the intermediate results. The more guard bits if you use, the more accuracy you get. Example, I will tell you. You are doing addition of these two. Okay. Otherwise, let us talk about subtraction. So clearly you can understand. When you are doing subtraction, recall how floating point subtraction will take place. First of all, exponents will be compared, correct? 10 power 0, 10 square. So this 0 is smaller than 2. Then we have to, add plus 2 to this. And appropriately we have to adjust the mantissa, recall. For that, we have to shift this decimal point to left side, correct? That means what? We should get 0.0239 into 10 square. Agree? So you just check it out. If you again multiply with 10 square, you get 2.39 into 10 power 0, correct? So this is the representation. But you have only 3 significant digits. 1, 2, 3. Then what about these two? That's why we require. If you really want this information, guard bits are required. So assume that let's say I am using 2 guard digits, okay, or 2 guard bits. 2 guard bits. Then how calculation will take place, we will see. Since I have 2 guard bits, then what I am going to do is I am writing like this: 2.95. This is guard bit. So in that guard bits I write 00 into 10 square. Here I write 0.02. Sir, you said you don't allow 0 here. Yes, I generally while representing I don't allow while taking the numbers, but when you are doing the operations like addition or subtraction, sometimes we have to lose that rule. Okay, but end of the day, while again representing the result back, then I will normalize the data. That means intermediate results or intermediate operations may make your data unnormalized. That is compulsory. Then only the basis we can make equal, right? So to make this as 10 square, then definitely this should be 0.0239. There is no other option for us. That's why I am temporarily making it unnormalized. This is unnormalized data. Now these are three significant digits here for me. Now what I do is 0 plus 9, 9. 0 plus 3, 3. Sorry, subtraction, right? I'm sorry. When you are doing subtraction, then what happens? From here we have to take borrow, right? 10 minus 9, 1. 9 minus 3, 6. 5 minus 2, 3. So 9 as it is, 2 minus 0, 2. So you get 2.9361 into 10 square. So now these two God digits we are using, right? Once everything is over, then we have to do truncation. Okay. So what is truncation? Because final result can occupy only 3 digits. Then these two God digits we have to now discard. While discarding, if you want to use anything, you want to get any information from that to accurately represent the answer, then you do whatever you want. Okay, what I want to tell you is, so these God digits are our information. Using that, if you want to conclude, otherwise if you want to modify your result to make your final result accurate, more accurate, then you can do. For that we use a method called truncation. So when you have more number of digits than what you wanted, then in this truncation there are two techniques, major techniques. One is simply cutting off, okay, chopping. One technique is chopping. Second technique is rounding. So rounding is very famous. Of course you do it. I mean, when in your childhood, when you are studying mathematics and floating point numbers, we did it. Okay. So I am explaining again that process, chopping and rounding. In chopping, simply we cut it like this. Simply we discard that God digits. Then you get what remaining thing, 2.93. Second one. So what is rounding? In rounding, what we do is we see the last that 2 digits. So these 2 bits you want to discard, right? That means you want to retain only these 3 digits. Then you have this to be discarded digits. In the to be discarded digits, take the most significant or MSB bit, most significant digit, which is 6. Then if it is greater than 5, 0, 1, 2, 3, 4 is one case, 5, 6, 7, 8, 9 one case. What we do is, because it is 6 which is greater than or equal to 5, remember this is one group, this is one group. If this number is greater, if it comes in this group, then what we do is we add +1 here. Okay, so then the result will become 2.94. Example, the number was like this, 2.93 something, 2147, whatever it is. So we want to use rounding again. See, this is this entire sequence is to be discarded. In that, the first digit we have to take and we have to see the group. If it is in 0, 1, 2, 3, 4 group, what we have to do is blindly discard them, no updation here. So this is the idea. Okay, now we'll see with one clear example. 2.178942. Second one 3.456237. So I am using again 3 significant digits. 3 significant digits. Then how to do the rounding? Focus on 3 significant digits. Now this is to be discarded. The first bit 8. So 8 is greater than or equal to 5. Correct. So remove that entire thing which we have to do, because these are all maybe God digits. Then you make this 2.17 to 2.18. Now here also this bit is 6. So which is greater than or equal to 5, then this 3.45 will become 3.46, which is quite simple. This is about rounding. But in the rounding there is one more point. What is that is? So example, you have tie. When you get tie, I will tell you, you have number 2.48 followed by, these are all God digits. In the God digits we have like this, 5, 0, 0, 0, all zeros. These are all God digits. So this is a special case. Whenever you have this kind of case where the first digit is 5, of course, but all the remaining digits are zeros. So that means what it is, tie. That means we say that, almost, so it is, I can say it's a dilemma. Should I add +1, otherwise should I keep 0? But general rule is what? If you blindly follow the general rule, if any number which is greater than or equal to 5 here, then we are adding +1, correct? But it's some extra condition, remember. In this special case, when your digit is 5 followed by all zeros, then we will be using a process called, so this is called tie breaking. There are a lot of ways we can do the tie breaking. So one of them is banking algorithm. Okay, in this banking algorithm, what we do is we just check the parity of the this digit. Okay, last digit. Mr. 8, are you even? Yes. If it is even, then we leave it. Directly answer is 2.48. What if it is odd? Example, let's say this number is 7. 2.475000. Then if we use same idea, if you use banking technique, then this value will be, first of all it will be checked, it is 7, right? Then we add +1. That means effectively we are adding 0.01. Let us add that. Then it would become 7 + 1, 8. So it would become 2.48. So finally the answer is 2.48. Understand? So this is about rounding techniques, and especially I am talking about IEEE 754 rounding standard. Okay, so this whatever I taught you, that is rounding. Generally in our regular arithmetic also we use, but this tie break can be done by so many ways, but IEEE 754 follows this banking rule. Okay, now let me summarize. The summary is like this. I am teaching all these things by remembering, otherwise by keeping what in mind, that IEEE 754 standard. So whenever you have 2.94325, okay, followed by 00000, now you are doing, let's say, rounding. In rounding procedure, what we are going to do is assume that, let's say, it is 3 significant digits again. So using the 3 significant digits, if you solve this problem, then 2.94 followed by, these are all extra bits. Now see the first digit. It is less than 5, right? Then definitely what we have to do, answer is 2.94. Remember it in rounding. Second thing, if this digit is 5 or more, then answer is 2.95. That is what I would like to say. If this digit is 5 and remaining all are zeros, then we use, tie breaking. This is called tie break. To do the tie break, there are various choices, remember, but IEEE 754 uses a choice called banking algorithm. In banking algorithm, we see this digit. That means last digit in the to be retained bits. We are going to retain all these digits, right? Out of them, last digit is 4. Is it even? Yes. Then answer will be 2.94 again. If it is something odd, then we will be adding +1 to that, and we make 2.98. That is the story about this rounding. Okay, so this is not only for decimal, so for your binary patterns also same kind of stuff will work. Okay, now I'll explain for our IEEE 754 format. Okay, now you understood what is guard bit and what is truncation, correct? So we use guard bits and truncation together to do this floating point arithmetic. Now we will go to IEEE 754 representations, and we try to understand the same concept.